So hello guys, welcome to this wonderful course. The title of the course is Engineering Maths Second 2. Your facilitator is none other than Mr. Mdlovu. Be taking you for this course. So what will we cover? So the course content, we want to study about differential equations, first order differential equations, separable, exact, linear, theory of solutions of the differential equations, second order differential equations, and nth order differential equations. What else will be covered? We are going to do applications of differential equations. Where can we apply those differential equations? Systems of differential equations will be covered on chapter 3 together with the stability, linearization, and then on chapter 4 we are going to cover partial differential equations. So what are the textbooks? Our main text will be shown as outlines, differential equation. This one you can be able to download it if you Google. And then the other text, this one is differential equations and dynamical systems. This one I will share on this learning platform. This might be difficult to download online, but this one, make sure you download this textbook. Right, so what is a differential equation? So you remember from our previous course we did calculus, where we were saying that if we have a function f of x and then we want to differentiate that function, if we differentiate that function we get a derivative. Right, now a differential equation is a result of differentiating a function. So what is a differential equation? So a differential equation is an equation involving an unknown function and its derivative. In other words, when we are solving differential equations, we are simply integrating or we are finding antiderivatives. That's how we solve differential equations. But these differential equations come in different forms. Where can we apply the differential equations? So differential equations can be applied especially when we are looking at the rates of change. For example, if we are looking at a function that changes, there is a change in y over change in x. When you've got those two variables, the respective change between these two variables can be measured, say, using a differential equations. Maybe the rate of change of flow of water out of a tank, septic tank, over time. So your dy will be the rate of flow, and then dt will be dt or x will be your time there. So we can use a differential equation to model that, or the rate of a degradation in a certain area, where you say the area is degrading at this rate over time. So that can as well be modeled using differential equations. So differential equations are used to model the rates of change. The rates of change. So we are going to start mainly about ordinary differential equations. Right, so the first order differential equation. So what is a first order differential? So a first order differential equation is a first derivative, rises as a result of a first derivative. And note that y prime is equals to f of x y, where f of x is a multivariate function. So it has got two variables, either x, y, or both of those variables. And also note that y prime can be as well written as dy dx. Please note that notation. example. So example, what is a standard form? So these differential equations can be written in standard form. You remember when you're doing your form 2, form 4, form 3, you did standard forms. Saying a to the power x times 10 to the power n. So as well in differential equations, we have got something like that, a standard form. So this is a standard form of a differential equation. So a differential equation in standard form should be written like this. So an example, if I want to write this y, bracket y prime minus 1 is equals to x in standard form, we remove the bracket or we expand there. This will be y squared, y prime minus y is equals to x, and this is y squared, y prime is equals to x plus y after taking that minus y the other side. Right, to remove this one y squared to that other side, y squared here it's multiplying, so when it jumps the equal sign it will come there and divide. Therefore we have managed to write this in terms of y prime is equals to everything else. This is the standard form. So therefore this is f of x is equals to x plus y over y squared. So this is the standard form of this equation. Right, classification of ordinary differential equations. So there are different types of ordinary differential equations, and we should be able to classify them. Why classify them? Being able to classify these differential equation will enable you to be able to solve, because if we can classify, then it means that we are in a better position to determine which methods apply in which type of an equation. Right, so the first form is the differential form. So a first order differential equation can be written in terms of differential form in the form of mxy dx plus nxy dy is equals to 0. Example, let's continue with the example that we looked at on our previous slide, where we had y bracket y prime minus y, which is equals to x, and we want to write this in differential form. Right, so first we need to write this in standard form. So you recall that this equation in standard form is equals to this guy. And again, you need to remember that y prime is the same as dy dx. So dy dx is equals to x plus y squared. Right. If I multiply dy by y prime and I multiply dx by x plus 1, this is what I'll get. I'll get y squared dy is equals to x plus 1 dx. Right. Taking x squared dy this other end, this will give me x plus y dx minus y squared dy, which is equals to 0, which is this guy. So congratulations, together we have managed to write this differential equation in terms of its differential form. Right, which other type of an equation do we have? You remember the Bernoulli, this guy, his first name is Daniel. He's famous with his principle of pressure. His principle actually states that the increase in speed of fluid occurs simultaneously with decrease in state pressure or decrease in fluid potential energy. So this Bernoulli equation deals with the rates of change between the fluid dynamics. Then you can as well use this Bernoulli equation to check whether the fluid is compressible or an incompressible fluid. So differential equations we find appreciation in fluid dynamics as well. Right, but let's continue with this Bernoulli equation. So a Bernoulli equation is an first order differential equation y prime plus px, where px is a function of x only, y, and then qx is a function of x only, y to the power n, where n denotes a real number. Right, so let's look into these following examples. Example number 1, suppose we have got x y prime plus y is equals to square root of x. Right, so I want to write this in terms of this equation. So first of all, you can see here I've got this x. I want to remove this x. So dividing by x throughout, I'll get y prime there plus 1 over xy plus is equals to 1 over x to the power half. Remember, square root of x is same as raising x to the power half. And this implies that y prime plus x to the power minus 1, applying laws of indices there, this will be x to the power minus 1y, which is equals to x to the power minus 1 times x to the power half. Then if you apply laws of indices there, when you've got the two similar base, and then the powers there we add. So if we add to minus 1 plus half, this should give you minus 0. You should be able to see this equation as a Bernoulli equation in the form y prime plus x to the power minus 1 y, which is equals to x to the power minus half y to the power 0. For Bernoulli equations, you should be able to see some of these things that exist there. For example, in this one, we have y to the power 0, which we applied the laws of indices. We know that y to the power 0 is 1. So we can write this in terms of Bernoulli equation, where px is x to the power 1 and qx is x to the power minus half, and n is equals to 0. Right, so how about the second one? Y prime plus 0y is equals to minus x to the power 5. So as you can see, this one, y prime, so this is this guy, and then this x plus xy to the power 5 looks similar to this. And then what we don't have is this guy. So if we don't have this guy, it means that the px there, this one is equals to 0. So that we multiply this, we eliminate this, is not there. So this guy, this equation 2 y prime plus xy5 is equals to 0 can be written as a Bernoulli equation in the form of y prime plus 0y is equals to minus x to the power 5, which therefore implies that px is equals to 0, qx is equals to minus x, and then in place of n we have 5. Right, so the third one, please, you can pause the video. For the third one, this will be classwork, so let's attempt this third one and share with your colleagues the solution to that one. Thank you.